This is Arizona desert, and right here, the most ambitious chip factory in America is rising. Inside, engineers just invented the most advanced microchip on Earth. But will it be enough? Enough to leapfrog TSMC and Samsung? I'm a chip design engineer, and in this video I will break down the genius behind this technology, how it will change every single device on Earth, and why it may either save or kill the company that built it. Subscribe to the channel and let me explain. Before we talk about the microchip breakthrough, we need to talk about where it's being born. Right now, a remarkable race is unfolding in the Arizona desert. Not just between companies, on the ground, between factories. And in many ways, it's even bigger than that. It's a clash between two different manufacturing philosophies. Factories, supply chains, governments, and billions of dollars converging into one race. And in Arizona, you can actually see that race taking shape. Here stand two most ambitious chip factories ever built. Intel's Fab 52 and just nearby TSMC's Fab 21, both trying to build the future of chips on American soil. And Intel's Fab 52 is the most ambitious one. The scale is staggering. Fab 52 rises out of the Acatillo Desert in Arizona. The complex covers roughly 2.6 million square feet. Building it took over 4 years and more than $20 billion. But those numbers still don't fully capture the scale. Over 600,000 cubic meters of concrete were poured into the structure. That is so much concrete that Intel had to build its own mixing plant on site, because local suppliers simply could not keep up. And that concrete was not for walls or floors. It was for the foundation of one of the most advanced factories on Earth. And that foundation had to be extraordinarily stable. And that's because semiconductor tools operate at atomic precision, and this is insanely precise. Imagine it like an astronaut standing on the moon with a laser pointer targeting my fingertip here on Earth. So this entire building sits on ultra-rigid base, engineered to absorb movement and isolate the machines from the outside world. And even building this foundation was a big challenge. In the Arizona heat, concrete can cure too fast and crack, so some of the most critical pours had to happen at night. Before this factory could make chips, it first had to survive the desert. Only then Intel started to turn this building in the middle of nowhere, in a desert, into a machine that transforms sand into silicon at atomic precision. At the heart of this process is the clean room, because in semiconductor manufacturing, cleanliness is everything. Here, I'm inside the factory, looking at transistors features only a few atoms wide. This particular one is just 30 atoms wide. As you can imagine, at this scale, even a tiny dust particle becomes enormous. For a modern chip, the impact of a single particle hit is comparable to a giant comet crashing into the Earth. One speck of dust, one invisible grain landing on a wafer is enough to ruin an entire chip. That is why every semiconductor factory is built around one place, the clean room. And in Fab 52, the clean room is enormous. Here it is, roughly 700,000 square feet of tightly controlled space sealed from the outside world. Keeping an area that large perfectly clean is an enormous challenge, especially in the middle of the Arizona desert. Outside, dust storms fill the air with billions of particles, but those particles must never reach the wafers. Inside the Fab 52, the number of particles allowed in the air stays close to zero. To make that possible, the cleanroom air is constantly purified. Massive fan decks push filtered air down from the ceiling. It glides slowly across the machines, then disappears through the floors below. Along the way, the air passes through ALPA filters, capturing 99.9995% of microscopic particles. The entire volume of air is being replaced hundreds of times every hour. Eventually, this room is 1,000 times cleaner than a hospital operating room. But surprisingly, the biggest contamination source isn't the desert. It's humans. Here you can see me entering the clean room, and the airflow already doing its job. A single person sheds thousands of microscopic skin particles every minute, so engineers wear full protective suits. The famous bunny suits. Hair and skin sealed, even breath isolated from the environment. And even then, human presence kept to a minimum. Most wafers move through Fab 52 entirely on their own. They travel inside sealed, overhead transport systems, gliding quietly from machine to machine. And all of this beautiful, brave new world exists for one reason: manufacturing the most advanced microchips on Earth. And these chips are built through thousands of steps: etching, deposition, lithography, cleaning, and then cleaning again. Which brings us to the next challenge. Water. Where do you get water in a desert? That's a very important question, because in chip manufacturing, water is as crucial as clean air. A single wafer can consume around 22,000 gallons of ultra-pure water during processing. That's roughly 18 swimming pools. At full production, Fab 52 will use about 9 million gallons every day. That's the water demand of an entire city, in the middle of a desert. So here, Intel had to build an entire water infrastructure around the fab. Right next to the factory, they've built a huge recycling and purification plant that recovers about 80% of the water used in production. Because the real challenge with water is not just the volume, it's purity as well. A microscopic chemical impurity can destroy an entire batch of wafers, which means every filter, pump, membrane, and sensor becomes a part of the manufacturing process itself. And without this massive water factory and recycling system, a semiconductor fab could never exist in the middle of the desert. And even with all that insane engineering, the desert keeps pushing back. Haboobs, walls of dust that swallow the horizon and threaten to breach the clean room. The desert doesn't care how much you spend. That is the hard reality of modern chip making. Only after solving all of that, the machines finally arrive. Fab 52 is filled with the most advanced machines humanity has ever built. Among them are extreme ultraviolet lithography scanners from ASML. Each one costs hundreds of millions of dollars, and these machines are used to print nanoscopic features into silicon. Across Intel's Arizona campus, there will be more than a dozen of such EUV systems. But lithography is only a part of the process. Inside this factory, there are hundreds of machines working together. Like atomic layer deposition systems that build films one atomic layer at a time. And then plasma etching tools that carve those layers into transistor structures. And both are critical to modern chip making. But inside this factory, among the tools, Intel has something even more unusual. The first commercial high-NA EUV machine. Each one costs about $380 million, weighs 180 tons, and must be shipped in multiple cargo flights. This is the most advanced lithography machine that exists. Intel was the first to get this machine, and it gives Intel something extremely valuable: lithography advantage. High-NA EUV can print features 1.7 times smaller than previous EUV systems. It enables up to 3 times higher transistor density. In simple terms, they might be able to fit nearly 3 times more devices into the same silicon area. And this entire factory was built to use that capability. And all of this extreme engineering exists for one reason: to build the most radical microchip technology ever attempted. Intel calls it 18A.
The first processor built with 18A technology, the most advanced process in the world.
And this is the most exciting note ever, because here Intel goes all in. And here the question is not anymore how cool their factory is, but what it enables and what actually changes inside the chip. Intel calls this node 18A.
This is a Mona Lisa. No, I think it's a Michelangelo, right? Sculpted in silicon.
The A stands for angstroms, a unit used to measure atomic scale distances. To understand how small that is, 1 angstrom is roughly 1 atom in diameter. And 1 nanometer equals 10 angstroms. So 18A, by its name, corresponds to about 18 angstroms, or 1.8 nanometers. At that scale, engineers are essentially engineering matter atom by atom. But here is a twist, with a tiny bit of disappointment, because actually those numbers, 18A, N2, 14A, they no longer represent the real dimensions of the transistor. They used to, in early semiconductors. Back then, the node number roughly matched the gate length of the transistor. It was something real that you could actually measure. Modern chips are far more complex. Today, the node name is mostly a label, because different companies measure and name their nodes differently. What really matters now is drive current and transistor density. In simple terms, it means how much current a transistor can push when it turns on. Think of it like water pressure in a pipe. The stronger the flow, the faster the next part of the circuit can switch. More drive current means faster transistors and better performance. This means modern process nodes are no longer defined by how small one feature is, but more how well the transistor perform and how densely engineers can pack them together. So the real question is not how small the number you see on the marketing slide, but actually what changed inside the chip. And in case of Intel 18A, wow, that's not the marketing. They actually changed 2 fundamental things. And this is something semiconductor industry never does. And it's insane to see how Intel goes all in here. In chip making, there is one golden rule. Change one major variable at a time. One big innovation per generation. Because if the process fails, you must be able to find out what caused the problem. With 18A, Intel broke that rule, and they introduced 2 major innovations at once, and that alone makes it one of the boldest process transitions in the history. And this is clearly crazy. But is it crazy enough to get Intel back to the top? The first change is the transistor itself. At its core, a transistor is just a switch, turning electrical current on and off billions of times per second. For more than a decade, the whole industry relied on one design, FinFET. It's powered everything from smartphones to supercomputers. But eventually, physics catches up. As we kept shrinking transistors, the fins had to become thinner and thinner. At some point, it became so thin that we started losing control. Electrons began to leak. Stability dropped. At some point, FinFET just stopped scaling, and they had to reinvent the transistor. And that new transistor is now being built here, inside Fab 52. Intel calls it ribbon FET. Instead of a single vertical fin, the channel becomes a stack of extremely thin horizontal sheets of silicon. Think of them like tiny ribbons stacked on top of each other. In FinFET, the gate surrounded the channel on 3 sides. In ribbon FET, the gate wraps around all sides, and that gives us far better control over the current. Without this architecture, transistor scaling was hitting a wall. Ribbon FET keeps Moore's law alive. But interestingly, ribbon FET alone is not the revolution Intel is betting the company on. The real deep break happens somewhere else, and we will deep dive into that in a moment. But first, if you're wondering what these little figures on my screen are, they are AI helpers by Sintra AI. Most AI tools just sit there and wait for your input. You prompt and hope for the best. Sintra is different. These AI helpers are proactive. They actually work for you. If you are not using it in your workflow yet, you are missing out. On busy days, I start with Wheezy, my personal assistant. I will say, Wheezy, help me prepare for today's meetings. It pulls from my email and calendar, gives me a clean summary. Who I'm meeting, what decisions are coming. For content and social media, there is Soshi. It drafts posts, keep track of what's working, and move things forward without me repeating context every single time. What makes all of this work is something called Brain AI. I had to set it up just once, my projects, goals, priorities, and from that point on, every helper already knows how I think. So when I ask for something, the response is spot on. And the coolest part that Sintra integrates with all the tools you already use: Gmail, Slack, Calendar, Outlook, Notion, securely with end-to-end encryption. You get more than 12 helpers in one platform, so you can focus on decisions that actually matter. If you want to save tens of hours every week, go to the link below and use my code INTECH at checkout to get 72% off on all plans. And Sintra have a 14-day money-back guarantee, so it's risk-free. Give it a try. Let's get back to Intel revolution. We already talked about Intel's new transistor design, but that alone is not the real revolution Intel is betting the company on. The deeper break happens somewhere else, something that had barely changed since the first integrated circuit: power delivery. And this is where Intel did something far more radical. They reinvented how power flows through the chip. Their new technology is called Power Via. For 60 years, every microchip on Earth followed the same basic blueprint. All the wiring lived on one side of the wafer. Signal lines, power lines, everything stacked together above the transistors. That design worked for decades, but as chip became more powerful and transistors smaller, it started to break down. What's interesting, inside every processor there are two different kinds of wiring. First, there are signal wires. These connect billions of transistors into logic circuits. They are thin, fast, and extremely sensitive. Then there are power lines. These feed energy into the chip. They are thicker, noisier, and carry enormous current. For 60 years, both systems were forced to live on the same surface. And that creates constant conflict, because this power network takes up space, injects electrical noise, and blocks the routing of tiny signal wires trying to connect the logic together. As transistors kept shrinking, this became a serious limit. And two major problems started to dominate. The first one, what we chip engineers called IR drop. As electricity travels through these tiny power lines, some of the voltage gets lost along the way. So by the time power reaches the transistor, it's weaker than it should be. The transistor still switches on, but it switches on worse, slower, and less reliable. And when that happens across billions of transistors, the whole chip suffers. The second problem is routing congestion. You can think of it like rush hour traffic on a highway. Modern processors contain hundreds of billions of transistors, and each one needs to connect to many others. That means an explosion of microscopic wires. But power lines do not shrink as gracefully as signal lines. They have to remain relatively thick to carry current. And over time, they take up more and more room, and making it harder to pack logic densely. The more advanced chip became, the worse the old architecture worked. For decades, the industry tried to manage this with more metal layers, better layout tools, and smarter routing algorithms. But the fundamental design never changed, until now. Intel decided to separate these two networks completely. For the first time in semiconductor history, power no longer comes from the top of the chip. It comes from the back side of the wafer. Signal wires stay on the front. Power arrives from below. This is Power Via. And from a chip design perspective, this is a huge deal, because it completely reorganizes how electricity flows through the chip. Power now arrives through tiny vertical connections from underneath, taking a more direct and efficient path. Intel claims that this innovation enables roughly 30% lower power losses and significantly reduced noise. At the same time, it frees more space for signal routing, which means more logic can be packed into the same area. So this is a real breakthrough of 18A. That's why it matters so much. But this is also why 18A is so dangerous. Because on paper, backside power delivery sounds obvious. So why did nobody do it earlier? Because building it is actually extraordinarily difficult. Because to do that, we for the first time have to process both sides of the wafer. Because Moore's law isn't just about transistors. It's also about whether the tools can keep up. Because at some point, the bottleneck shifts to equipment. So what does this new manufacturing process actually look like? First, the transistor layers and signal wiring are built on the top of the wafer, in the standard way. Then something unusual happens. The wafer gets flipped and bonded to a support wafer. After that, most of the silicon is ground away from the back until only a thin layer remains. Only then can engineers drill microscopic holes and fill them with metal to bring power from below. These become the new power connections, feeding electricity from backside of the wafer. And that process is incredibly hard, because once the wafer is turned and thinned, it becomes incredibly fragile, more sensitive to temperature changes, harder to handle, harder to process reliably, and the machines have to be recalibrated. It means new chemicals, new steps, new metrology, and entirely new manufacturing recipes all have to work together. And this is why we started with factories. This is why factories matter so much, because this is no more about the design. It's about who can do this surgical work at scale. And that is where Intel made its biggest gamble. Before 18A, Intel had originally planned an intermediate node called 20A. The idea was sensible: introduce one major innovation first, do the learning, then add the next breakthrough later. But Intel cancelled 20A. But when you're already behind, the pressure to accelerate becomes enormous. So Intel skipped this safe transition. They just skipped the learning and went straight to the node that would decide the company's future. And very quickly, the difficulty showed up. Lithography alignment issues, material deposition problems, multiple new failure mechanisms interacting all at the same time. This is exactly the kind of stacked complexity process engineers try to avoid at any cost. And this is what makes 18A such a fascinating story, because Intel didn't just push the new node, they reinvented 4 things at once: the transistor, the power delivery system, the factory, and the manufacturing flow. That's not a routine node transition, that's a semiconductor moonshot. So where does it actually place Intel with respect to the rest of the industry? The closest process node is actually TSMC's N2, but the difference between two strategies is striking. TSMC's N2 follows a cautious path, one innovation at a time, prioritizing yield and reliability. Intel did the opposite. They just introduced ribbon-fed transistors and power via backside delivery altogether. And Intel is already shipping these new chips, a year ahead of TSMC. The first product in 18A Panther Lake processors are now in production. TSMC plans to introduce its version later with A16. This means that for a brief window, Intel is the only manufacturer running the most advanced architecture at scale. Meanwhile, TSMC's Arizona fab is starting with more mature nodes, first N4, then N3. Still extremely advanced, but not the newest technologies TSMC runs in Taiwan, in their mother fab. TSMC is also preparing to adopt high-NA EUV machines, but Intel was the first to install these machines for production. Which means inside Fab 52, Intel holds something rare. A real hardware advantage. And that matters. But that is not enough. Because the hardest part of semiconductor manufacturing is not the tools. It's making the entire process work. Thousands of steps clicking together in perfect sync, at scale, with high yield. That's the real test. In semiconductor manufacturing, everything comes down to just one number: yield, a percentage of chips on a wafer that actually works. At high yield, a fab prints money. At low yield, the economics collapse. When production at Fab 52 started, the early A18 yields were below 10%. The first Panther Lake processors showed defect rates far higher than expected, and the reason traces back to the same decision. But even with this yield, Intel could still ship chips, but these chips would be way too expensive. And that's where the dream collides with economics. Slowly, through months of learning, the numbers started to move. Progress was gradual, but real. Careful, meticulous engineering. Step by step, Intel began to claw its way forward, until finally the company could start shipping products. In late January 2026, the first Panther Lake processors built on Intel 18A began shipping. And that mattered, because for the first time in many years, Intel's most ambitious process crossed the line from experimental ambition into the real product. Clearwater Forest, Intel's next-generation data center processor, also starting production soon. So the story is no longer whether 18A is real. It is real. The real question now is whether that's enough, because solving yield is only the first problem. Then there is another big problem: trust. Because Intel manufactures chips, but at the same time they are competing directly with many companies they want as foundry customers. Imagine sending your most valuable chip design to a company that builds a direct rival product. Intel ships Xeon processors. AMD ships EPYC. And that makes for a difficult conversation. And TSMC never had this problem because they do not compete with customers. Intel does. That built-in tension has a name. It's called the IDM dilemma. And even leading-edge tech doesn't make that tension disappear, which is why companies like AMD remain fully committed to TSMC. For Intel Foundry to gain broad adoption, Intel would effectively need to step back from competing in the very same market it dominates today. That is politically and commercially impossible. So the conflict remains. TSMC wins trust just by not competing, but Intel has to fight both physics and the human nature. Now, there is a very important exception to this: NVIDIA. NVIDIA recently committed roughly $5 billion to Intel's foundry. But this is not a full manufacturing shift. For now, they are focusing on test runs and mostly chiplet components, not complete GPUs. Why? Because NVIDIA has its own problem. TSMC is full. AI demand is pushing the company's advanced capacity to its limits. Some estimates put utilization well above 100% for the next couple of years. So NVIDIA needs a backup option, a second manufacturing pipeline. And Intel's fabs in Arizona and Ohio offer exactly that. It's less a vote of confidence and more a strategic hedge. NVIDIA gains access to additional capacity. Intel gains credibility, and the US government gains something even more important: domestic AI manufacturing capacity, which brings us to the next challenge: volume. Even if technology works, and even if yields improve, a fab this expensive only makes sense if it stays busy. These factories need real utilization, real customers, and long-term production. That is where the wider foundry landscape becomes critical. TSMC still has the strongest ecosystem, the deepest manufacturing experience, and the highest level of customer trust. Samsung stays in the race as well, fighting for selective design wins. Intel, meanwhile, has something neither competitor fully has: political momentum in the United States. Governments are increasingly worried about how much of the world's advanced computing depends on a single geography, which makes diversifying semiconductor manufacturing a national priority. And as the global AI build-out accelerates, supply becomes just as important as technology. which means Intel challenge is no more purely technical. It's commercial. Can they fill the fab? Can they win customer trust? Can they stop companies from defaulting to TSMC? This is a real battle now, and it will ultimately decide Intel's future. This is why the entire industry is watching these stories so closely. Today, most of the world's most advanced semiconductors are manufactured by one company, mostly in one place. And that concentration creates enormous risk. For the United States, the stakes are even higher, because the semiconductor industry was born in America. From the invention of the transistor at Bell Labs to Silicon Valley, Intel, AMD, and NVIDIA. But today, the most advanced manufacturing happens somewhere else. This is why 18A matters so much. If it works, the impact goes far beyond one company. The whole supply chain becomes less fragile. And the world gains a second serious player capable of building the most advanced chips. There are already reports that NVIDIA is testing GPU designs on Intel 18A. No production commitment yet, but even testing matters, because if NVIDIA ever chose Intel as a meaningful manufacturing partner, the semiconductor landscape would change overnight. This is how big this could be, and this is why this story matters. Not because Intel used to be great, but because the modern world would genuinely benefit from another company capable of manufacturing the most advanced chips. Though I'm still really rooting for Intel. Right now, Intel may have built one of the most advanced manufacturing processes ever attempted. But in semiconductors, being first is not the same as winning. 18A is one of the boldest manufacturing bets in decades. And right now, Intel may briefly be ahead, but the rest of the industry is moving very fast. TSMC's next generation is coming. Its A16 node will combine gate-all-around transistors with backside power delivery. Samsung is also delivering a similar transistor architecture and a backside power network. And the entire industry is converging on the same blueprint for advanced chips. So the question is simple. Can Intel turn this early lead into a lasting advantage? Or the rest of the industry will be able to catch up before the window closes? That's what we are about to find out. Make sure to subscribe to the channel. Now watch this deep dive on the memory war and the unexpected winners, or this episode where I go inside the microchip factory to show you the most advanced transistors under the microscope. Love you guys, and I will see you there. Ciao.